In this video, I'm going to show you a mind-blowing example of the connection between the electric and magnetic forces. You're going to see exactly why magnetic fields are generated by moving charges. Let's quickly go over the basic facts. Naturally occurring magnetic materials were known to the ancient Greeks. And by the 12th century, the Chinese were navigating using compasses made out of magnetic lodestone. From a modern perspective, we would say that the compass needle was aligning with the Earth's magnetic field. The magnetic field is an abstract way of thinking about the force that a magnet exerts on other magnetic materials or on charged particles. The motion of the interior of the Earth generates a magnetic field, and this magnetic field protects us from harmful radiation in space. The Sun emits a number of charged particles, for example electrons and protons, and these are deflected by the Earth's magnetic field, away from causing harm in the lower atmosphere. The magnetic field produces a force on moving charges. A stationary charged particle will not feel a force from the Earth's magnetic field. We can see this from the mathematical expression of the force. The force is equal to the charge of the particle, Q, times its velocity, times the strength of the magnetic field, B. So you can see that the larger the velocity, the larger the magnetic force. And if the velocity was zero, then, well, the magnetic force would be zero because the force is proportional to the velocity, and therefore a stationary charged particle experiences no force from the magnetic field. In contrast, the electric field acts on any charged particle, whether they're moving or not. Our experiences with the electric force began even before we knew about magnetism. Ancient peoples knew that rubbing an amber rod with cat's fur would cause it to attract other objects around it. We now know that the process of rubbing the amber rod with the cat's fur is transferring electrons from the cat's fur onto the amber rod. And so the amber rod gains an excess of electrons, and since electrons are negatively charged, the amber rod as a whole becomes negatively charged. The cat would become positively charged. And again, we've invented this abstract idea of the electric field to help us describe the forces that a negatively charged or positively charged object exerts on the charged particles surrounding it. Because this amber rod is now negatively charged, it's going to attract positively charged particles. So a proton that's just sitting in empty space is going to be attracted towards the rod. Even if the proton were moving, its motion would be bent towards the rod. An electron would feel a force away from the rod, and so its motion would be bent away from the rod. And again, we have a simple expression for the force produced by an electric field. The strength of the force of the electric field is equal to the charge of the particle multiplied by the magnitude of the electric field. But until the 19th century, we didn't know that there was a connection between these two forces. Sure, they both acted on charged particles, but electricity was produced by the action of rubbing two objects together, and magnetic materials were dug out of the ground. It was a man named Hans Christian Ørsted who provided the first evidence that the electric and magnetic forces were connected. And he was performing experiments on electric currents. In order to produce an electric current, you create an electric field in the wire, and you usually do this using a battery. And this electric field causes the charged particles in the wire to move. In the case of a metallic wire like copper, the positively charged particles are the nucleuses of the different copper atoms, and these form a lattice inside the wire, a rigid lattice, so these particles can't move in response to the electric field. They're fixed in place. But the electrons that surround these nuclei are free to move, and so the electric field is able to move these electrons, and the movement of the electrons is called an electric current. And it's the same electric current that delivers power to your household appliances. And Ørsted discovered that if he held his compass next to the wire, the needle of the compass was deflected when there was an electric current flowing. So the electric field in the wire produces a current, and the current in turn produces a magnetic field outside the wire. And because it's a magnetic field, that means it's going to interact with any moving charged particles near the wire. So if a proton is moving parallel to the wire, in this case it's going to be deflected towards the wire. And if an electron is moving parallel to the wire, well, it's going to be deflected away from the wire. And this really was a huge discovery that led to a flurry of results that explored this connection, the connection between the electric field and the magnetic field. And this research eventually culminated in Maxwell's equations of electromagnetism. And Maxwell's equations give you a formula for how the magnetic field changes in response to an electric field and how an electric field changes in response to a magnetic field. But it doesn't tell you why they do it. The actual mechanics behind the relationship between the electric and magnetic fields is incredibly surprising and at the same time very beautiful. Maxwell's equations were the inspiration for Einstein to produce the theory of special relativity, and actually it's special relativity that hides the secret that is the connection between the electric and magnetic fields. For those of you that know special relativity, this could come as a big shock because special relativity is a theory about objects that are moving very fast, and in our case, nothing appears to be moving very fast. We have a current in the wire, but the electrons moving through the wire under the influence of the electric field are actually moving very, very slowly. And even the charged particles passing by the wire are moving at mundane, everyday speeds. Nothing is travelling anywhere near 10% of the speed of light, which is really the threshold where we need to start using special relativity. But by the end of this video, we're going to derive an equation that describes the magnetic force on a charged particle moving near a wire using only the formulae of electrostatics, that's the electric field produced by static charges, and special relativity. And given that we can find our answer using special relativity, what's the first thing we're going to do? Well, we're going to transform ourselves into the frame of reference of the particle which is experiencing the force. That means that we're going to start moving so that we're alongside those particles moving outside the wire, and we're going to try and see what's happening from their perspective. So once we start moving at the speed v, which is the speed our proton and electron are moving at, well, they're going to be stationary. And the positive ions in the wire? Well, they were stationary before, but now we've started moving at the speed v. They're going to be coming towards us at that same speed. So it appears like all the ions in the wire are going to be rushing towards us at this speed v. And what about the electrons? Well, they were moving at the speed v0 towards us originally. But now that we've started moving at speed v as well, then surely the speed they're coming towards us is just v plus v0. But actually, this is where it gets a bit tricky because special relativity takes us outside the realm of our everyday understanding of time and space and velocity. And special relativity tells us that the velocities of objects don't add in the simple way that we think they do. For example, if the particles on the outside of the wire were moving at some crazy velocity, like 3/4 the speed of light, and the particles inside the wire were also moving at 3/4 the speed of light, then when we add those two velocities together, we get something that is 1.5 times the speed of light. But the whole premise of special relativity is that nothing can travel faster than the speed of light. So it necessitates that adding velocities doesn't happen in the usual way. And instead, if we want to add two velocities, in our case v and v0 together, we need to scale the resultant velocity. It's easier if I just show you the formula. The actual velocity that will be produced is v plus v0 divided by 1 plus v times v0 over c squared, where c is the speed of light. Ordinarily, when v and v0 are very much smaller than c, then the number in the denominator, 1 plus v v0 over c squared, is going to be very, very, very close to 1. And so the velocities will appear to add in the normal way. We'll have some answer that's very, very close to v plus v0. There are some other weird properties that special relativity introduces. So what are these other weird properties? Well, the first is that the force due to the electric field experienced by our charged particles is different depending on whether we're moving alongside the particle, that means we're in the reference frame where the particle is stationary, or whether we're watching the particle move by us. That's the frame of reference where the positive ions in the wire are stationary. And the ratio of those two forces is given by something called the Lorentz Factor. And the Lorentz Factor is a very important parameter in special relativity. Things like space and time, when we start to move very fast, are squashed and stretched by this factor gamma. And so it is in the case of the force provided by the electric field. If we measure the force as we're moving alongside the particle, and then stop and stand still and watch the particle whiz by, and then measure the force that we've measured the second time is going to be a factor of 1 over gamma times the force we measured when we were moving alongside that particle. And I've already mentioned the other strange fact that we need, and that is that once we start moving, the distance between objects gets squashed. Space gets squashed. And space gets squashed again by the factor 1 over gamma. So that means that suppose my table has a length d0 when I'm sat in front of it. As soon as I start to move past it, the length of that table is going to shorten a little, and the length that I'll measure as I'm moving past it, which we'll call d, is going to be equal to the original length, d0, divided by the Lorentz factor, gamma. And since the Lorentz factor is always going to be greater than 1, then the new length we measure is actually shorter than the length we measure when we're sat next to the desk. And this discussion applies equally well to the particles in our wire. So supposing the positive ions are a distance apart d0 when we're sat next to the wire, when we start moving at the speed v alongside the charged particles, we're going to be moving past those positive ions, so the distance between them is going to appear smaller than it was before. And it's going to be smaller by the factor 1 divided by gamma. And the same is true of the electrons, but the electrons are moving at speed u, and u is faster than the speed v, so the electrons are going to be squashed together even more. And the distance between them, instead of being d0, is going to be d0 over gamma of u. Oh, or is it? Because actually, if you think about it, when we were sitting next to the wire, the electrons were already moving. And so, because of that motion, they were already closer together than they would be if they were stationary. To find out how close they would be together if they were stationary, we need to multiply by gamma instead of dividing by gamma. So that means when stationary, the electrons would be d0 times gamma of v0 apart. And that's the number that we need to divide by gamma of u to find the distance between them when we're moving along at speed v outside the wire. So can you see that because the distance between the electrons is now less than the distance between the positive ions, then there's an overabundance of electric charge in the wire. There's more electrons in a length of wire than there are positive ions in that same length of wire. And so we have a situation exactly like we had with the amber rod. Our length of wire has more electrons than it has positive ions. And so when we're moving alongside it at this speed v, it appears negatively charged. And we know that a negatively charged object has an electric field, and the electric field lines point in towards the center of that object. And so if I were a proton moving alongside this wire, I would be attracted towards it because the wire is negative, and if I were an electron moving alongside the wire, I'd be repelled away from it. Since we're also moving at the same speed as this electron and proton, they're just going to move towards and away from the wire. But if we're sitting in our stationary frame and we see these particles go past, we're going to see them either bend towards or away from the wire, and we're going to say that they've experienced a force due to the magnetic field produced in the wire. But if we were to move alongside those charged particles, alongside the electron and alongside the proton, we'd actually see the wire as not having a magnetic field, but having an electric field, because the wire would appear negatively charged to us. So here is the really deep connection between the electric and the magnetic fields. A particle that appears to be influenced by a magnetic field is actually just experiencing an electric field. Isn't that great? What a beautiful connection between the electric and the magnetic fields. And who'd have thought that it would be special relativity that holds the answer? Now, some of you might not take my word for it. And so we're actually going to derive the force on these charged particles. It's going to involve a page or so of equations though, so don't worry if you don't feel like you can follow along with it. You already have the physical insight behind this connection. Now, from the perspective of an observer, stationary with respect to the wire, he would say that the wire has produced a magnetic field. And so the force on those charged particles moving past the wire is going to be equal to Q times V times B. And what's the strength of the magnetic field produced by the current in the wire? The strength of the magnetic field is equal to mu0, which is just a constant, so you don't really need to worry about it, times by the current in the wire, I, divided by 2 pi times r, where r is the distance away from the wire that the charged particle is. So that's the ordinary way of thinking about this problem. But we now know this extraordinary way of thinking about it. From the perspective of the moving charges, the wire itself is negatively charged. But exactly how much is it negatively charged? Well, to find that out, we need to know exactly how much more densely packed the electrons are than the positive ions. First, let's see if we can simplify gamma of u. Well, we know it's a horrible mess. It's equal to 1 divided by the square root of 1 minus v plus v naught divided by 1 plus v naught over c squared, all squared, and then that whole thing divided by c squared. We can take out a factor of 1 plus v naught over c squared. And after a little algebra, you'll see that we get 1 plus v naught over c squared times by 1 plus v naught over c squared all squared minus v plus v naught over c squared, and everything to the power of minus 1 over a half. Expanding out the brackets, this all simplifies to 1 plus v naught over c squared multiplied by gamma of v times gamma of v naught. That looks nice, actually. That's much simpler. And now we need to use our new simple formula to find out the density of the electrons in this wire. But first, let's look at the charge density of the positive ions in the wire. The density of the positive ions in the wire is going to be equal to the density of the positive ions in a direction perpendicular to the direction of motion. Let's call that sigma, multiplied by the density of the positive ions in a direction parallel to the direction of motion. The density of the positive ions in the direction parallel to the direction of motion is going to be equal to 1 divided by d naught over gamma of v. And so after rearranging, that's sigma times gamma of v over d naught. And now the density of electrons in the wire is going to be equal to sigma times by 1 over d naught times gamma of v naught all over gamma of u. And once we substitute our expression for gamma of u into the equation, what we have is sigma times gamma v over d naught multiplied by 1 plus v naught over c squared. So using our expressions for the charge density of the positive and the negative ions, we can combine them to find the net charge density, which we're calling lambda. Lambda is going to be equal to the density of the positive ions minus the density of the electrons. And substituting in those values gives us minus sigma over d naught times gamma of v times v naught over c squared. And this factor of sigma over d naught is simply the charge density of the positive ions in a stationary frame of reference. So let's call this lambda naught. And this is telling us exactly how much more negatively charged our wire is than positively charged. And in order to find the force on the charged particles outside the wire, we need to know the strength of the electric field produced by that negative charge. And we know that the strength of an electric field for a long rod is going to be equal to the charge density divided by 2 pi epsilon naught r. And epsilon naught is just another constant, but it's a constant that's related to mu naught in a special way. But for now, let's just replace lambda with our expression, and that's going to give us gamma v times v over 2 pi epsilon r c squared multiplied by lambda naught, the new factor, times v naught. But lambda naught v naught is the charge density of the electrons times their speed, which is equal to the current in the wire. And the current in the wire is denoted by the letter I. And if we want to know the force generated by that electric field in the frame of reference that's stationary with the wire, then the electric field has to be divided by the factor of gamma of v. So the force is going to be equal to Q times the electric field of the rod divided by gamma of v, which is going to be equal to Q times I divided by 2 pi r epsilon naught c squared all times v. But now this special relationship between epsilon naught and mu naught comes in. Actually, c squared is equal to 1 over mu naught times epsilon naught. And we substitute that in the equation, and we see that the force on the particle is equal to Q mu naught I over 2 pi r all times v. And that's exactly the formula that we saw earlier. The force on a charged particle by the magnetic field of a wire carrying current I. But we've derived it using special relativity and electrostatics. So if you ever forget the formula, you can derive it from first principles. And in fact, actually, if you know what I'm talking about when I say Fleming's right-hand rule, you can do away with Fleming's right-hand rule if you can just think quickly about the direction the electrons in the wire are moving and the direction that the charged particles outside the wire are moving. And you can determine whether they'll be deflected towards or away from the wire. I hope you enjoyed the video. This is my first physics video, And I'm still a relatively new YouTube channel, so every subscriber really gets me excited. So if you've listened this far, I hope that means that you found it entertaining. So please like the video and share it with anyone you think would be interested.